Okay, so hello everyone. This will be the content for a class on Monday, November 21st. Okay, so this will be our new chapter after we spend sometimes to finish off the trigonometry. Now we are going to do the new chapters, which is the polar coordinates. Okay, now what is polar coordinates? Okay. So the polar coordinates, the system is they are using the distance and directions based on the pole, okay, or we call them origin in this case. Okay, and to begin with, let me draw for you. Let me give you the picture. Oh wait, okay. Let me give you this one. Okay, so to begin with, the polar coordinates, it start by an axis called polar axis, this axis. Okay, so we are going to move the point P, this point. Okay, so we are going to move this point all around this polar axis. And how do we do that is we are start by taking some turns from this polar axis. So start from here, and then based on how long our radius, this r, yes, suppose this is our r here, and then we have some angle measurement theta, and then we move out according to the theta here. Okay, so let me draw here that it's going to be according to this axis we call the polar axis. This O is we call the origin, or sometimes we call the pole. Okay, so this point P is having the coordinate of r and theta. So we are writing the coordinates as a radius and the angle theta. Okay, now if we look at, if we could imagine we are moving the point P in every way we can. For example, we can move P going here, going here, going here, and you are going to notice that the distance is always the same. The radius is always the same, which means that this radius, it seems to be always positive, right? So what's happened if our radius is negative? Well, in polar coordinates, in polar system, it could happen. Okay, the r can be, it can be negative. So let me write here, can be negative. But how we visualize the negative radius? The visualizations will be, if we take this, okay, the visualizations, although we have, for example, we have the same angle here, movement, but if we say the radius is negative, then the radius will be behind the one that's supposed to be there. So for example, we have radius is -3, for example, which means if this is r equal 3, if this is r equal 3, then the one behind here is the negative part. Okay, we are going to see in practice how it works. Okay, I think that will be better, but for now let me just explain like that. Okay, okay, now let's try to plot some polar coordinates. For example, we are going to plot some plot the coordinates 1, 3 over 4 pi, and then 3 minus pi over 6, and then 3 pi, and minus 4 pi over 4. If you want to take your time to understand, you can pause the video and try by yourself and try to imagine how it looks like. Okay, But let me just give you directly how it looks like based on our picture here. Wait, not this one, this one. Oh wait, not this one. Wait. Oh, I don't have. Well, let me draw one by one. So 3 over 4 pi. Let me start with the polar axis. And 3 over 4 pi will be takes time, maybe around here. It's because this is pi over 2, this is pi over 4, maybe around here. Okay, yeah, maybe around there. And just let's say this is r equal 1, and then the point here is p1 3 over 4 pi. Okay, what if the measurement of angle is negative? As I mentioned, I think in trigonometry, if you have a negative angle, then we start always from the polar axis. Okay, this is the polar axis. The minus means that the angle will move clockwise. So rather moving from here to here, we are moving to here, okay, there. So we are going to maybe around this angle. Well, it's not really proportional, but let's just say this r is 3, and we could say this p is 3 and then minus pi over 6. Okay. And what happens if it's going to be 3 pi? It's greater than 2 pi, which is the full circle. So 3 pi means, so this will be this will be this, okay. And let me move out a little bit, move there a little bit, okay. So 3 pi means, let me take this polar axis, and imagine that the 2 pi is start from the polar axis. So we move like this. This is 2 pi, and then we move one more time until here. This is pi. So the total will be 3 pi, and this will be our point. Let's say that is the p3 3 pi. Okay, let me maybe adding the 3 over 4 pi here to denote the angle. This will be 3 pi, so total 3 pi. Okay. The last one, now we have the negative form, the negative radius. So always start from the polar axis, and the angle is just pi over 4. So pi over 4, if this is pi over 2, maybe around here, that will be the angle. Let me make a little bit longer for the radius, maybe here. Then our radius will be going here, the opposite sides of the radius. So every time you have the negative radius, this will be your radius, your true radius here. Okay, so this will be negative 4 pi over 4. So where is pi over 4? The pi over 4 is actually here. Okay, that's how you draw the polar coordinate system. Okay, so that's the definition. Okay, definition of the polar coordinate system. And then one thing that is, I believe, also important is this part. When we have r theta, as mentioned here, if we make the r negative, and then if we take the theta plus pi, we could see that it's actually going back to the same value, that this is p. Okay, So let me start with if what we will be. Okay, what will be if we have, for example, the P, we know that from this point of view, if we have the radius is negative, we are going to have the opposite side, right? So let's say we have the same angle theta, but radius is negative. This will be the place. Okay, maybe let me add more steps here to make it similar, maybe here. So this will be another P, just to make some additional information for you. This is negative r and theta. Okay, and it's actually the same as when we take r and then take theta plus pi. Okay, now I hope you understand what the point of view in this description. So the negative, or you plus the theta with pi, it's always giving you the same or similar similar notions or similar characteristics in the system. Okay, if you see how it moves away from the polar axis. Okay, I think that's for the first part, the definitions of just the definitions of the polar coordinates. Okay. Okay, now we are going to go to more details on the polar coordinates, especially how to convert the polar coordinates or the rectangular coordinates to polar coordinates. Okay, so we are going to start with the relations between polar and rectangular coordinates. Okay, as you know, or maybe if you don't know, if we have the x and y axis like as usual, this is y axis, this is x axis. If we put some coordinates, let's say coordinates from this 0, 0, and then maybe let's say this is 1, 1, and maybe another one maybe here, 2, 1, and then this will be 2, 2, and so on and so forth. Then we could imagine that if we could pinpoint all the point, let's say we are going to see that all this aspect, all these points, they will create if we have a distance by 1 unit, we could have let's say this is 1, this is 2, and this is 3, and you can see that this is what we call the rectangular coordinate, because all the points that we can put on this axis, these two x and y axis, they will create a rectangular shape, right? Now if we look at the polar, the polar start with the polar axis like this, and we move out our points starting from this polar axis. We move from this, let's say this point within certain radius, and we have, let's say, some angle measurement. Let's say this is our angle here, and we state that our point is based by the r theta. This is r, this is the angle. Okay, and while the x-axis, it's clear that the point that we want to put is their x and y positions. Okay, and another note that for the polar coordinates, we could see that we are going to have some circular circular, let's say, circular shape. Okay, if we could take sometimes to check, and if we change all the radius with the same, let's say the same angle, you could see that they are having a circular shape like that. And we could imagine that if we want to move out our point, and we move out our point like this, we change our radius, we change our measurement, and we could have all this possibility of this point of the polars, right? The polar system. So this is the polar system. This is the rectangular system. Now, how the relations between these two? What is the relations? Okay, I think I already given that in the trigonometry, especially for the unit circle. It's actually quite simple. So we just look at the triangle, this triangle here, and we could imagine from the xy axis, we could imagine that there are certain angle here, okay, and then certain distance that we take as our radius, and then our point in this xy like this is also our points in the polar system, which denotes by r and theta. Now the question is how to relate this r and theta with x and y. We've learned before that in our triangle here, that if we have the cosine theta and sine theta, the cosine theta, we always start with x over r, and r is a constant. We can say it's a constant, okay? And sine is y over r. So we could take this x and y inside this, within this r theta variables, and we could exchange and convert the polar to rectangular, or from the rectangular to polar. So we could say that from the polar we could exchange the x and y, and they are becoming r cosine theta and r sine theta. And from the rectangular to polar, we could relate to the circle equations like this one, and then relate that the tangent theta is y over x. This y over x will determine the theta. This determine theta through the tangent. Okay. Okay. Perhaps we could take sometimes for examples. Okay. So if we take the rectangular, let's say we have the 2, -2. This is rectangular coordinates, and we want to convert to polar. So we know that x is 2, y is -2. So first we could take the r squared. Let me write all the notions, all the formula for this one. So we have 8. So we could get r is 2 square root of 2, or -2 square root of 2. Remember, we might have a negative radius in polar, okay? And then tangent theta is -2 over 2, or -1. So remember, whenever we have tangent negative, tangent is positive on the third quadrant, right? So on the first quadrant. Okay, sorry, I forgot the first one. So on the second quadrant and the fourth quadrant, the tangent will be negative, as we can see here. So we could conclude that the tangent, or the theta, now will be having 3 over 4 pi and -pi over 4. This is on the second quadrant. This is on the fourth quadrant, right? So we could have the points on polar. First is 2 square root of 2 negative pi over 4, and the second one is negative 2 square root of 2 3 pi over 4. Okay, I think it's best to be drawn, okay, and see how it will be visualized like this. So again, they are although seems the notation is different, or the how to write is different in sign and in science, like positive, negative, and the angle measurement. But when we take some measurement, they are actually on the same points. This is just confirming what we have in the previous page. Okay. Okay, another example. If we have x squared equal 4y, we have these equations. We want to express in polar. So we could take this and we could imagine the r cos theta inside the equation x. So we substitute 4, and we have this, and then we can solve the r. And then this will be 5 sine theta cosine squared theta, and then r is 4 secant theta tangent theta. This will be our equations for polar. So we call this a polar equations. So polar equations will be denoted by r equal to some functions in theta. Okay, this is what we call polar equations. We are going to have a lot of contents regarding these polar equations later on. If you take the calculus 2, we will discuss more in true for these polar equations. Okay. Now another examples that I think we are going to emphasize within these sections is conversions from polar to rectangular. So polar to rectangular. So for example, we are given the polar equation, let's say 5 secant theta. Okay, and we know that this is 5 over cos theta. We can simplify first and take this r cos theta equal 5, and we know that r cosine theta is x. So we could say that x equal 5 is our equations in rectangular. So the vertical line is our equations. Okay, so that is for 5 secant theta. And then if we have r equal, let's say 2 sine theta. Okay, how to solve this? How to make this make it equal? First is to take multiplication with r. Okay, so we multiply both sides with r, because we want to use the formula of the r squared equal 4 2 r sine theta. So our r squared is this, and we know that the x squared plus y squared is r squared, right? Now this will be y, right? 2y, so x squared plus y squared is 2y. And we can write this, and writing all the circle equations, and simplify this, we could write a circle equations. So we are having a circle with center 0, 1. Okay, remember the circle. Okay, Okay, and lastly, the last example here, if we have the r equal 2 plus 2 cosine theta. Okay. Okay, now this will be similar with the previous questions that we are going to multiply with r. So this will be our equations. And we could also write down the circle equations like this. And then this will be 2x, right? So you could exchange r squared with 2r plus 2x. So we could solve the circle equation simplified. But then this will be not really solvable in our case here. But let's say we are going to force this out. Okay, let's say we are going to force this out and take the squared like that. And of course, the way we have this in rectangular coordinates is just the way it is like this. We cannot really can be simplified after like this. If you can try to expand the equation, but it's not really that useful. So we could just stop here and we could see the equation. So the points what I want to emphasize in our examples here, when you are trying to convert from polar to rectangular, we are going to convert the r theta into xy. So you need to exchange all r theta in the equations and change into x and y. Like in our case here, up until here, we still have r. And then how to remove the r? Well, we need to square the r. So we need to multiply by r. Well, if we multiply by r, we will have another r here. So it's best to take the squared, and then the squared will be exchanged to x squared plus y squared, which is, I think, going to be true in these equations. And it's going to exchange all r into x and y. Okay? So that's our goal. Okay, we need to exchange r theta and then change all with x and y. Okay, and it's also going to be true if we want to convert from xy to r theta, then we need to change all xy and then change to r theta. Okay. Okay. Now we'll move on to how to graph of polar equations. At the beginning, we have been shown that the rectangular coordinates and polar coordinates, we could differentiate those by this grid. Okay, we have the rectangular grid for the rectangular coordinates, like you see before. I draw something like this, and we have a lot of grid. Okay, which means that we have a lot of squares, okay, in between of units. Okay, in between of units to describe the x-axis and y-axis. Okay. Now, when we have the polar, then we should have the polar grids. These grids will help our sketch. Okay, will help our efforts to draw polar curves, to understand how it relates, how it moves. Okay, and it easily point out the positions using the polar coordinates. Okay, polar coordinates, as you know, it is going to be the radius and the theta. Okay, r theta. That's the description on the coordinates itself. Okay, now if we want to draw polar coordinates, for example, if we are just given, remember the polar coordinates or the polar curves is described by the r and theta in one equations. Okay, or for example, if we could tell that we have r equal 3, this is also polar curves. Okay, r is a constant 3. What does it mean? It means that in every angle, in every full circle, or in every measurement of theta, the radius will be a constant 3. Okay, so if we draw, for example, if we draw through, or maybe if we take this, okay, if you take this, and then we say that, okay, 3 is here, okay, 3 is here according to this grids. So what we are going to do is we are going to make this move along all these segments from all of the possible theta. Okay, and we have a circle. So this is our polar curves r equal 3. Okay, but let me draw here. I have the picture already, so I just put on, and this will be our r equal 3. And we could also think the r equal 3 into the rectangular forms. So we could square this to left and right hand. So we have r squared equal 9, and we know that r squared is x squared plus y squared equal 9. So what is this? This is a circle centered at 0, 0 with radius equal 3. The same thing, okay? So I hope you get what the connection are. And then we could also have a polar curve that describe through, let's say, theta equal pi over 3, which means the theta becomes a constant. And how about the radius? Radius could be any numbers. It could be 1, it could be 2, it could be 3, but it doesn't describe within this equation. So that means we just stop the line until the measurement of pi over 3. Which means that if this is, let's say this is a pi over 3 here, so we could have a really long line that goes through this grid. And this is line theta equal pi over 3, okay? So we could draw this and giving the description. All right. Okay. So we have this line pi equal pi over 3. Theta equal pi over 3. So what is theta equal pi over 3? If we remember that we could also can write down the rectangular y over x equal tangent theta. Okay, and tangent theta is now is tangent pi over 3, which is the square root of 3 tangent 60, right? So we have y equals square root of 3x line. So this is a line equation. Line equation with slope is square root of 3. Okay, so I hope you can get familiar with the polar curves. Okay, the next one, let's get in more a little bit next level. Okay, so what if we have the r equal to sine theta? Now perhaps to get the best understanding on these polar equations, we could see how it relates to our theta. So let's describe that in a table, and then we take some value of theta from 0. Let's say we start from 0. Okay, 0 sine theta is 0, so it's 0. And then pi over 6 is half, sine theta is half, so it's become 1. And then pi over 4 is half squared of 2, and it's become square root of 2 because multiplied by 2. And then pi over 3 is half square root of 3. The half is cancelled, so it's square root of 3. And we get all until, let's say, until pi. Okay. Well, we could increase like maybe from pi to maybe 3 over 2 pi and then 2 pi. But this will be just repetitions. Okay, we will see what could have been. Okay, now how to take this into our polar curves. So we could imagine a polar grids, and then we could points out each point from theta equals 0, and then theta equal pi over 6, and then until theta equal pi. Okay, but let me just give you the results already. So this will be the results. So we are starting from, let me use the different color green. So we are starting at theta equals 0. Okay. Theta equals 0 is getting r equals 0. So it means it's going to be in the first centered like that. And then theta equal pi over 6, r is becoming 1. So if we see this 1 unit here, this is 1. And then this will be pi over 6, and radius is equal 1. Okay, if you can see that this is also connecting to here, right? And then we have square root of 2. Well, we could take this 2 here, 2 here, and perhaps square root of 2 is around here, and this will be pi over 4. Okay, and then pi over 3 is a square root of 3, so it's going to be in between 2 and 3, a little bit a middle. So you could like maybe it's around here, square root of 3, because 3 is here, 2 is here, right? So maybe it's around here, square root of 3, and square root of 2 maybe around here, right? Okay. And then pi over 2, it's 1. So 1 multiplied by 2 is 2. Oh, wait. Should be not 2 and 3. I got a wrong idea. So this will be 2. Okay, 2. Yeah, square root of 3 is 1 point something. Square root of 2 is also 1. Yeah, 1 point something. So it should be between 1 and 2. Okay, not. Okay, and then this in between here is 1.5. So to be exact. So 2 is here, and then another part is going to be, so 2 pi over 3 will be equal to this, right? This will be equal to that. This will be equal to that. So we could just see the height should be the same. So this will be the same with this. This will be the same with this, okay? And this will be the same with this. And then until the pi, so this is pi here, right? This is pi. So when we have pi, the radius is 0. So we back to the original equations, or original 0. Okay. Original when theta is 0. We could move to, for example, we could move to the next part, like we maybe take from here another angle. This should be pi plus pi over 6, right? Or we could say that this will be what it is, 7 over 6 pi. But this will result in negative. The sign is negative. This is equal to this. Or this will be negative half. And in r will be negative 1. So 2. So this will be negative 1. What's happened when we have negative 1? We are going to have the opposite sides. Which means, let me emphasize this so you can understand what I mean. That this point also, the blue point, the same point at this green one, is also appear that this is when we have negative 1, 7 over 6 pi. Okay, as we also discussed this at a few previous pages, that when we have radius is negative, for example, it should be here, it should be around here, okay, should be around here, but because of negative, we are going to go back, and then we put our points into the same positions as when we have pi over 6. Okay, I hope you get my idea. So all the things in the third quadrant is basically the mirror on this first quadrant. And when you do the same thing with the fourth quadrant, you will see the same mirror with the second quadrant. Okay? Okay. This is really important, and even this is important when you are going to move on to learn the calculus 2, which we will have more discussion on the polar coordinates. So if you miss out these sections, you will get confused on the calculus 2 problems. Okay, so I hope you understand all the settings, all the settings. Okay. Okay, now we are continue our sketching curves. Okay, sketching a polar curves. Now, if we would like to sketch a graph of r equal to plus 2 cosine theta. Okay, what should we do now is we can graph the plot. Okay, so instead taking the table like this, we could draw a plot that is going to describe the r and theta, its relations. So we could take it from theta equals 0, which is 0 here, cos 0 is 1, so 2 plus 2, so it's 4, 3, 2, 1, and we could take this for all possible values of theta, and we could think that theta also it goes for the special angle. Okay? And to make it simplify, we could take this as in the special axis in the polar axis or the polar grids. Okay, and then we can transform or transfer all these points into our polar grids. So let's draw the polar grids. So let me draw the polar grids. So let me take this into here, and then the polar will be having this the set of process. Okay, so we start from, let's say we start from here, theta 0 and theta pi over 2. We could think this numbers. Okay, from the theta equals 0, it's 1. Okay, so we start from around here. This is theta equals 0, and then we could think perhaps taking some pi over 4 here, and then imagine the pi over 4 inside the cosine. We have 2 plus square root of 2, so 2 plus square root of 2. So if this is 4, okay, 2 plus square root of 2 is around 3 point something. So probably if we take the pi over 4 here, and maybe, yeah, this is the point. Okay, and then we could also think the pi over 2 here. It's the this is the radius equal to, right? Okay, so we have these steps. Okay, and then we take more process. Okay, we take it from pi over 2 until pi, and we could see that the result is they are going back into the center of this polar axis, which is 0, 0, or in our case, in the polar, this will be pi, or not pi, it's supposed to be r theta. So r is pi, r is 0, and theta is pi. Okay, and then what's next is we could take the this angle here between the pi and 3 over 2 pi, and we could see that the value is increasing, and then if you could see the slope also increasing. Okay, if you could see the slope like that, and as a consequence, we could see some change in our r. Okay, we can see change on our r. Okay, you can see change up until we have this 3 over 2 pi. Okay, so 3 over 2 pi is going to be the cosine will be 0, so it will be equal to 2, radius equal to 2, and then the last part is we are going to see this part 3 over 2 until 2 pi. Okay, and we see that it's going to be increase significantly until it's reaching the 2 pi. 2 pi is going to be going back into our cosine 0, which is 1, and that is when the radius is 4. So we see that we can have this kind of structure. Okay, and this is what we call it's going to be looking like a heart shape, right? Heart shape. So we could say that this is cardio, like in cardio in the biology, cardioid, or its heart shape form. Okay, so every time you have this 2 plus 2 cosine theta, or we could say a plus a cosine theta, this is our cardioid, or plus minus. We can also plus minus. Okay. Also, we could have the sine. This is also cardioid, but the difference is between cosine and sine, we will see later on. Cosine and cosine is always going to the left and right. So cosine is going to be like this and like this, while sine is going to be like this or like this. Sorry. So cosine is left and right, sine is always top and down. We will see also later. Okay, so this is the cardioid. Okay, next is, what if we have the r equal cosine 2 theta. Okay. Now, as usual, as we see from the cardioid's process, we could draw the rectangular. Okay. And let me just cover this for a while so you don't have any distractions. So first is we take some special value. Let's say we have from pi over 4, pi over 2, 3 over 4 pi, and then up until 2 pi. Because we have this 2 inside, and remember 2 means we have a different phase. Okay, different phase means we will have to see the periods will be the one periods will be different. Okay, so we are going to see 2 periods now, because we have two kind of graph. Like this is the first one, right? And the second one is this. Is that right? So we could transform or take this rectangular coordinates for the r and theta, and we could relate with our polar grids, okay, as usual. So if we take the let's say, let me just draw from the polar axis. Okay, this is the polar axis. Okay, let's start from theta equals 0. So when theta equals 0, its cosine is 1. So let's say this is the radius 1. So we start from here, and then we take the cosine pi over 4, which going to be makes the radius is becoming 0. So this intrigued much, because when we have the interval from 0 to pi over 4, we could take the pi over 6, maybe pi over 6 is good example. Let's take that as our example. So pi over 6, if we take the into our equation cosine 2 theta, it will be pi over 3, right? Pi over 3 is 60. Cosine 60 is half. So we could take that as our angle also. So if we take the angle, probably if this is, let me draw. Let's say this is pi over 2. Okay, and then this will be This is pi over 4. Okay. And let's say we have, yeah, let's say this is pi over 6. So if we take that, and then we have this is r equal 1 here, and then perhaps it's half, it's going to be here, okay? And then we could see that, we could imagine that this is going to be true like that, okay? Up until cosine, this is pi over 4, okay? This is pi over 4. So at cosine pi over 4, it's going back to the 0. And then the next part is, we are going to see that in between of this interval from pi over 4 until pi over 2, the value of the r is negative. So we are going to see that at cosine pi over 2, the r is negative 1. So if we take the pi over 2, so it's supposed to be here, but since it is a negative, we are going to go to the opposite side. So which means we are going to go to this line here, okay? Or if we take the, so let me pull out the line, and this is 3 over 2 pi. So we are going to see that the pi over 2 will be here. So this will be negative 1 pi over 2. Okay. So what does it mean? It means that it's going to be here. Okay. More or less. Okay. But I think I'm not drawing it really proportion to proportion. Let me draw clearly. So this is supposed to be having the same amount of value as the radius one. So let me take this maybe around here there. I think it's better. Yeah. So we have here, okay, and then from pi over 2 until 3 over 4 pi, this one here is still at the negative r. Okay, it's still at negative r. So if we doing the, again, let's take a look what we have here, and then let's say we have another angle here. This is theta equal pi. So let's say we start from pi over 2, and then 3 over 4 pi is going to be here. This is 3 over 4 pi. And at 3 over 4 pi, it's going to be 0. So we could see that because it's supposed to be here, this area, but because of the negative, then we are going to see that it's mirrored through this area. Okay, so we are going to see that it's going to be like that. Okay, yeah, it should be proportional, symmetrical, but let me just draw this as illustrations. I will give you the final result later. Okay, and then after that, we move on to see the 3 over 4 pi until pi. We see it's going to be in positive sides. So we are going to see that it's supposed to be here. This positive, right? This is the actual interval that we want to see. So we are going to see it's going to be like that. And then until a pi to 5 over 4, it's the same. It's still positive, and we have like that. And then 5 over 4 until 3 over 2 pi, we see that it's negative. So it's supposed to be here, but since it's negative, we are going to mirror through the negative sides of over there. So we are going to see that it's going to be like this. And then if you follow all the intervals, we will see that it's going to be leaving it like this. And we have we call this as the rose curve or four-leaf rose. Okay, so four-leaf rose, we say this is the kind of curve we have. And the final results, as you maybe observed before, I accidentally take it at the beginning. So this will be the results. Okay, so I hope you understand, especially when we have the negative part here, it's going to be the opposite sides when we sketching the curve. Okay, it seems a little bit complicated when you draw, putting in the polar axis and in polar grids and how it moves. Okay, it seems like a complicated process, but at the end we'll see that all the polar curves has a pattern, and we are going to see that pattern. Okay, and at least we will have four different main polar curves. Okay, from the circle, the rose like this, and the cardioid, or we say the limacon, and the lemniscates. We have four different patterns. Okay, for all of that. Okay, now we are going to look more. Oh, by the way, I haven't written yet here that we could write the rose curve as a cosine and theta, and also for the sine. The difference is on the difference of the faces, or the angle. If you see, this is the cosine. The sine version will be like this. More or less like that. Okay, but there's something that need to keep in mind, that we are having the so both of this, okay, is we call the n-leaf roses. So it depends on how many n. Okay, so n-leaf rows. So if n is odd, if n is odd, the number is the same as the row's number. Okay, and so this is first. The second, we call 2n leaf rows if n is even. So for example, we take the example on 2 theta here, which means it's even. Then the rows we have is 2n leaf rows, so 4 leaf rows. But when we have, for example, cosine 3 theta, we will have 3 leaf rows. Okay, now to help these illustrations, we are going to have a symmetry concept. Okay. We call it symmetry in polar. There are some notes for this symmetry, because we know the symmetry in rectangular coordinates, right? When we plug in negative x, and then we see that if the result is having the same as the original equation, it means that it is an even function, right? And if we take if we get the negative of original equation, we are going to have an odd functions, right? And we have also symmetry and asymmetry, right? And in polar, we have something a little bit different. That if we have the symmetry, okay, there are 3 tasks, okay, at least 3 cases or 3 tasks. If a polar equation is unchanged when we replace theta by negative theta, then the graph is symmetric about the polar axis. Okay, we will see the figure later. And second, if the equation is unchanged when we replace r by a negative r, or theta by theta plus pi, then the graph is symmetric about the pole. And if the equation is unchanged when we replace theta by theta minus theta, replace theta by pi minus theta, then the graph is symmetric about the vertical line theta equal pi over 2. Okay, now what does it mean? Okay. I think I get to the picture to help us to the best our understanding for visuals. So the first one, so this was the first one, the second one, the third one. Okay. So symmetry about the polar axis. So if we replace, for example, well, you could imagine that if this is your original positions, and we replace the theta with negative theta, of course you have a polar curve, polar equation, r equals something something. And if you replace that, and if we get the same positions or the same r here, okay, and the negative theta is again against the it's negative of the positive. So in the polar curve or polar coordinates, we take the positive value of the theta when we move theta from polar axis going forward to counterclockwise. Okay, so we move from this part going that part, we take that as a positive theta. The negative theta means we take the from polar axis and we move going to the clockwise. So we move here. Okay, that's the negative theta. And it says that if we take and if we see that it has the same value of r, which means that it is symmetry about polar axis. This is a polar axis. Okay. Okay. Now if we have this, okay, I think this case is true for the rose, right? This rose curve, if you remember what we have here, okay, we have the negative part of the radius, right? So when we take that and it goes by, it's actually the same theta. Okay, it's actually the same theta here, but the radius becomes negative. So it goes to these positions. Okay, so we say that this is symmetry about the pole. So you could imagine the pole being in this part of the middle part, this one. This is the pole. So you could imagine that is like positions of the yeah, like yeah, like a pole. Yeah, like a pole, like it goes through your eyes. Okay, and we see that the positions is they are opposite each other. Okay, and then the third case is when we take the theta. Okay, we take the theta and we taking the pi minus theta. We take pi minus theta, and then we see that it will symmetry about this theta equal pi over 2. Okay, it will help us to let us know how to draw the polar curves better. Okay. Okay, now from this symmetry task, we are going to check, okay, how we can graph our equations for polar curves, especially for something that is going to have some repetitions, and we are going to see also the pattern, okay, on the polar curves. Okay. Now the cardioid that we've done before, we call the general form of that is a limaçon. Okay, limaçon. Yeah, the below C there is some curly tail that is, I think, in Latin. Example of limaçon is 1 plus 2 cosine theta. Okay. Now if we take that And if we make the same or similar approach with when we have this cardioid, we draw this r and theta graphs, right? So let's do the same thing and graph this r equal 1 plus 2 cosine theta in rectangular. In rectangular, we have these relations within the r and theta. Okay, so we take the theta 0, okay, and we know that it's 1 plus 2, so it's going to be 3. Okay, and then especially at the cosine negative, which is the cosine pi. Okay. The cosine pi is -1, so it's become -2 plus 1. So it's -1, so it's going to be here, right? So there are some interval on this part of graphs that is going to be in negative interval. Okay, that is negative interval, right? So while we are compare with the previous cardioid, we don't have any negative interval. Now we're going to see what does it mean or what is implications in the graphs. Okay? If we see the cardioid or the cardioid, we see that it's perfectly having like a heart shape, and we have the closed graph completely, right? We could say that. But in Limason, we are going to see that the negative parts will getting some loops. Okay, so we are going to see some loops on the curves itself. Okay. So if we take the so if we replace, let's say, replace theta with negative theta, so the equations become 1 plus 2 cosine negative theta. Remember, when we have cosine negative something, negative theta, it means that this is the quadrant 4, right? The quadrant 4. It goes to quadrant 4, and quadrant 4, the cosine is positive, okay? The cosine is positive, so it's the same thing as 2 cosine theta. So there's unchanged situations, like we did in the symmetric test, that we have unchanged situations, then we have a symmetry about the polar axis. Okay, so we say that this will be symmetry in polar axis. Okay, now if we take another steps, and let's say we find zeros or the roots for the r. So let's say r is 0, and we're going to find where does the theta will be. And we see that the theta will be -1/2, and the angle will be 2 pi/3 and 4/3 pi. Okay, this is when the cosine theta is -1/2. Okay, and from here, this is actually what we have here. Okay, so we have the 2 pi/3 on that positions, and 4/3 is in here. Okay, this is 4/3 pi. So alongside this interval, the radius will be a negative value. Okay. And then after that, we can take this into our sketching. So we could start with taking the polar axis, okay, and then taking another axis as well. That is for the theta. So this is theta equals 0, theta equal pi/2, theta equal pi, and theta equal 3/2 pi. And then when we take this, for example, the the first step is taking the theta equals 0. So theta equals 0, let's say this is 1, this is 2, this is 3. So let's say we have start from here, and then we take that, and when we say we are going to have the cosine pi over 2, for example, that is 0. So r is 1. Okay, so r is 1. So we still have something that is going to be probably here's 1 is here. So we are going to have something like that. Okay, and then we know that the zeros at the 2 over 3 pi. 2 over 3 pi is going to be around here. Let's say this is 2 over 3 pi. So we are going to take that and make it into these positions. Okay. And then we take more. That is when it's 0. And then the negative part between the 2 over 3 and 4 over 3, well, we could take the pi. So when we have pi, the position is -1. So remember, when we take -1, so it's supposed to be -1 is, or 1 is supposed to be here. This is pi, right? So we have the opposite. So it should be going to be here. Okay. And then take the same approach for 4 over 3 pi. 4 over 3 pi is going to be 0. So this whole thing here, the negative part, is actually the loop. And then we take the approach like that, and we move on, and then we have this. This is, we call the limmason. Limmason with inner loop. Or we could say, or we could draw that as this limmason like this. This is I think more proportional. My drawing is, well, not really proportional, but the way we see how it moves, okay, it's the same. It's the same, okay. So this is limmason of inner loop limmason. Okay, so limmason has a structure of r equal a is a constant plus minus b cosine theta, or r a plus minus b sine theta. Okay, and we are going to see the relations, the ratio of a and b, because we could change that into some numbers. Okay, in cardioid, if a is equal b, then it's become cardioid. Okay, now if we see more examples to come for the limmason in general, we could have this. This is if we have r equal 1 plus c sine. Okay, remember sine, I have mentioned before briefly that sine will have a top and bottom relations. The cosine have the right or left. Okay, so if I take some example, okay, let's take the example for example 2 cosine theta like before, and then we have -2 cosine theta, and then we have also another one 2 sine theta, and then r -2 sine theta. Okay, to make it easy, let me draw. Okay, this is not rectangular, this is a polar. So this is 0, pi over 2, pi, and 3 over 2 pi. Okay, now if we have 2 cosine theta, we know that this will be our, this will be our, or maybe we start from sine. Okay. We have sine before, right? We have sine before. This is 2 sine theta. We have here, bottom here, we have -2 sine theta. Okay. Now if we have here, this is 2 cosine theta, the right side, and if we have another circle here, this is -2 cosine. Okay, now the Sine, cosine, they are related to how the patterns will be. So sine positive is in top, sine negative is the bottom, cosine positive is the right side, this cosine is negative is left side. Okay, now that is actually true also for all polar curves. Okay, so when we have the cardioid, for example, cardioid have the last time we have the 2 plus 2 cosine theta, right? 2 plus 2 cosine theta. The cardioid becomes like this, right? Now if we have 2 minus 2 cosine theta, this will be the cardioid, like that. What if we have the sine? Let's say we have this negative sign like that. Negative is bottom side, like this. And if we have a positive, this will be positive. Okay, so that's the same thing. And if we have this 1 plus c sine theta, and if we take the c as large as possible, we see that the inner loop is getting large. Okay, large inner loop. And when we take that as small as possible, we take slowly, and we see that the gap between the inner loop, the interval, is getting smaller up until when they are equal 1. When they are equal 1, then it's become cardioid. Okay, it's become cardioid. Okay, now we are going to see the summary of what all of the possibility of the polar curves. So we have a circle, like a normal circle, r equal constant. We have a circle also for the sine and cosine. It's the top down equations. So for example, here's the other one. Or maybe let me draw like that. And the cosine is having the left and right situations. Okay. And we can also have a spiral, but I'm not really explaining the spiral too much. Okay, I will leave that for you to find out yourself for the spiral. But this is, I think, the most important one, the sine and cosine. And then we have the limason. Okay, so they are already giving you some patterns. So we have a plus minus b sine theta, a plus minus b cosine theta, and a and b should be in a positive signs. Okay, and of course plus minus can be depends on situation as well. So first is the limason with inner loop that we have discussed before, and then if we take a equal b, it will be cardioid. And if we take a is greater than b, we have some sort of a dimpled limason. Okay? And if we have a at least equal to 2b, and then more maybe larger than that, then we have a convex limason. It's going to be like a circle. It's going to be like a circle. Okay? Unless that there are some differences in this radius, right? Differences. And then we have roses. For example, we have a sine and theta, a cosine and theta. So we have n leafed rows if n is odd, like this one. We have cosine 3, cosine 5. It's 3 roses, 5 roses. But if we have even, then we have 4 leaf rows for cosine 2 theta and 8 leaf rows for cosine 4 theta. And then we have also Lemni's skates. Okay, I haven't told you more about this, but this is just as simple as when we have r squared, we know that we can have r squared, and we have a, and we know the a squared. We can identify a squared from the equations, and it has this 2 theta. Okay, it can be sine or cosine. When we have sine, we will have this kind of shape, and cosine, it has this like an infinity symbols. Okay, if you'd like to imagine or visualize. Okay. Okay, now we move to the parametric curves. We are going to have the parametric equation or plane curves and parametric equations. Okay, so let me just take these definitions. So we have f and g is a functions defined on interval I, and we can set these f and g, and we set the t as another variable. Okay. So both of f and g, they are also function of t. Okay, and then we can write that x is actually our f of t and y is g of t. Okay, so we call this t is our parametric or parameter, the parameter t. Okay. And this x equal f of t and y equal g of t is our parametric equations. We can think this problem like if we visualize. Okay, take example that t is time, okay, and x, y is coordinates, okay, coordinates in rectangular. So for example, if we want to like visualize the motions, okay, the motions of like kinematics, like you've done in physics previously, right? So let's say we have this like this curve, okay? So we are going to have for each t, like for example t0 maybe start from here. This is x, this is y. Let's say t0 start from here, and then maybe t equal 1, t equal 2, t equal 3, and as we move on, as t increases, the positions is also change. Okay, so we could think t as like a time, okay, and x and y is just the positions, the height. So if, for example, if we want to sketch and we want to have like, for example, the we are given the equations, that is t squared minus 3t, that's for x, and y is t minus 1. Okay, to solve this problem, or to sketch, okay, to sketch the question is sketch the parametric equations. So we could start with take times, evaluate all x and y with some possible t. We can start t from, maybe take t from negative numbers, and then we could have, let me just put the drawer here, okay, just to see how it looks like. Okay, we start from t equal negative 2. Okay, if we t negative 2, x becomes 10, y becomes negative 3. So t negative 2 is here, okay, this one. And then if we have t negative 1, it's here. And then t equals 0 is here. Okay, and then we take all with all possible t, okay, and then we see that we have this kind of curve. Okay, we have this kind of curve, and remember, because we start from this negative 2, then we need to draw the arrow, so it has an arrow, so it has a directions. Okay, it has a directions from where to where. Okay, if you maybe if it is different type of parametrics, okay, perhaps the arrow could also be different. Okay, and then if we replace, okay, if we replace this t, so t replaced by 2t, the x becomes 2t and then squared minus 3 2t, and then y becomes 2t minus 1. Okay, we could take this. Okay, let me write here in the next page. So x is 4t squared and y is 2t minus 1. Okay. And if t is changed to negative t, then we have x so we have x is t squared minus or plus now. This is minus, so this becomes plus, and y is negative t negative 1. Okay. Now, if we change to this new parametric equations, the results, if we trace into our curve, it's the same curve, but look at the direction and look at how the points will be. Okay, so the left one is this part. Okay, this is when we replace t to negative t. See the arrow. Now the arrow, it seems going into the opposite directions as we compare with the first one, right? So it has the opposite directions. And then the second curve, if we take the t, the possible t from negative 1, 0, 1, 2, we are going to see that if we see that this is, we can say that the conclusion is it's twice the curve, okay, twice the first curve, the original curve, because we changed the t into 2t, right? Or we could say twice as fast, while the first one here is the opposite direction. Okay. Okay, let me write again or maybe giving you the copy of this same functions for parametric. So let me copy. Oh, wait. Not, okay. Okay. Now we have this as our copy. The same functions, the same parametric equations. Now if we take this t and then rewrite these equations, become that. And then we substitute to here. And then we solve this. And we have these new equations. Now these equations, if we take to, if we factor out, get that, right? And of course, if we try to draw the curve, that is the same curve like the previous one, like this curve here, okay? And we will have the y as its zeros, for its x. Okay, so we have this is -1 and 2, and it's supposed to be the same like that. Yeah, the same curve. So it is a parabola. Okay, so with this method, we call the method for eliminating parameter. This is also one method to know how the shape of the curve will be. Okay, so the idea is just to substitute one of the t into the other one, okay, the other equation. So if we want to substitute from y, and then we are going to rewrite them in t equations and then substitute to the x. Another example is if we have let's say x is cosine phi and y is sine phi, and t is a positive value or equal to 0. If you want to describe this, remember that we can take this x and y and then take it into squared. So if we take these two squared, we are going to have this cos squared t plus sine squared t. And of course, because of the identity, this will be equal 1. So we are going to have x squared plus y squared equal 1. We are going to have a circle at centered at 0, 0, and has a radius equal 1. Okay. So we could draw that into our situation here, and we have a circular motions. Okay, this is a circular motions. So the parametric t, or the parameter t, it can be signifies the directions of our curve as well. Okay, so we start from t equals something, for example, from 0, and we plus or we add the t pi over 2 pi, and then we see circular motions. Okay, we can see circular motions. It's especially if this is related to some measurement using some angle. Okay, like in polar. Okay, now another example. If we have x sine t, y equal 2 minus cos squared t. Well, first, we could start from this y. Okay, let me write again. 2 minus, and we could write cosine squared with 1 minus sine squared. And then we could directly, for obvious reason, we can see that this has sine and x is also sine t. So we could write this as 2 minus, or we could write 1, 2 minus 1 is 1, plus sine squared t. And we could write that as 1 plus x squared. So we have a parabola 1 plus x squared, and easily we could draw that as well. Here, okay. It's just an x squared move upwards 1 unit. Okay. So this is 1. And then we could also see that since the sine t will be in between -1 and 1 for its minimum and maximum value, so our x will be also start from -1 to 1. So the curve will have some limit here. So the curve will not exceed this point. Okay? So this will be not possible. This part will be not possible. So let me erase this. Okay. And since sine is periodic, So we have this arrow, the yellow directions, the yellow direction here. It can be going forward, backward, forwards, backwards, like that. Okay. Okay. Another interesting parametric equations is the cycloid, the cycloid parts. Cycloid is if you have a circle, like maybe let's say, let me draw a circle here. Okay, imagine we have the circle, and the circle will have a motion, circular motions along this straight line. Okay. So we have another circle here. So imagine that the circle is moved from this one position to 2 positions. So this is the same circle. So we move from 1 to 2. Okay. Imagine that when the circle moves, let's say we have a point P at the bottom right there. Imagine that the point P along this straight line, if this is having a circular motions, the P will move to here, 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 and here, right? And eventually for positions number 2, the P will, well, we could say probably it's move away from the original positions, right? So let's say we take, let me draw some transitions here. The transition to see how the P moves. Okay. So let's say the P moves here in the transitions, and then maybe another transitions here, just to make sure that we are able to understand what the cycloids means. Maybe the first not really that far, maybe a little bit closer, maybe here. Okay. And this part is maybe here. So this red dot is the P, and then lastly, the P is maybe around here. Let's say that is our P. If all possible P positions in every movement of the circle, if the circle has a certain circular motions where P is changing its positions, and if we connect all the dots, okay, we connect all these P positions, we could have certain shapes. Okay. We could have like this, and go over here. Like that. And perhaps if we try to move out this circle again to another positions on the right side, okay, perhaps it's going to be like that. Okay, well, it's not really good proportion, so let me draw a good one and give you a good picture. So this is, okay, what cycloid means. Okay. So the green color, not green, sorry, the blue color is our circle. This is the first position. So it has a circular motion, go over there, and it's move out, and see the second positions here. The point P is moved to this side, right? And then we move again, and let's say we move about here, and all this line or all this red curves is a connection of all P that is moving away. And if we draw all of that P, we get this kind of pattern. We call this cycloid. Okay. So I hope you get the idea of cycloid now. Okay. Now to make things interesting, what does this cycloid means in terms of, well, the parameter or parametric? Okay. We could see, okay, if we take some parts of between this movement of circle, then we could, let's say, break down what it is, okay, in more detailed view. Let's say we have this P still here, this P, okay, that's a P. And then we could relate to the parameter of a circle, which has a radius. This is the radius, right? We take the radius as A, and we have a certain theta here, and take some line here, okay, to make our coordinates, okay, for this center of the circle. This is the coordinates. The A theta is this part here. And A is this A here, okay? So A theta is actually, so maybe let me start over. Let me start over to make it easy to understand, okay? So first, this yellow line start at the beginning, the P, okay? This original P start from here. P is starting from this point, right? Which means that all of this yellow line, they are all touching the straight line 0 to some t here, right? So the first assumption that we are going to make, okay, the first assumption. So assume that the 0t or OT is equal to the arc of PT. PT is the yellow line like that. Okay. So the arc of PT, if you remember the circle, how to find the arc is basically the radius multiply, or if we have this is a theta, so the arc is theta over 2 pi or maybe not taking 2 pi. I think still directly is still okay. So r theta is the arc, okay? So this OT is equal to A theta, okay? This A theta here. That's why we have the coordinates for C, A theta, and A. Because this is also A, right? The height, also A, okay? And then we are going to describe the cycloid from point P, from the coordinate P, from here. Okay, let's describe the cycloid. So the cycloid has 2 components, of course, the x and y. It's a coordinate. So x is, if we see from the picture here, that we can write down all the relations, is equal to OT minus PQ. Okay. OT is A theta. PQ is related to the sine or the angle theta. Okay, we could draw the triangle, bad triangle. Okay, let's say this is our theta here, right? This is C, this is P, this is Q. So sine theta is equal to PQ over PC. PC is A, okay, so PQ is A sine theta, okay? Now we have this A sine theta, or we could write A theta minus sine theta. That's the first component. The second component is Y. So we write Y, let me move here. So Y is equal CT, okay, minus CQ. CT is A, and CQ, we could imagine that is a cosine theta, but let me write here as a note, okay? So cos theta is CQ minus or over PC. And we say that CQ is PC is A, so A cosine theta. So we are having the A cosine theta, or A is 1 minus cosine theta. So we have this two component that is X, A theta minus sine theta, and Y is A 1 minus cosine theta. So this will be the component of cycloid, okay? The cycloid will also be our discussions in the next calculus 2. And I think our polar equations or polar curves, polar coordinates, and parametric equations or plane curves, I think should be sufficient for now for our basic math courses. Although there are several sections that I've skipped for our class, but I think all the components or parts on this chapter, I think they are all has been done. So we finish here. So we're going to have perhaps, because I will be off for a few days, starting from 26th of November until 30th November. So we are going to take another online content, okay, for our class. And after that, so next December, we will have our offline classes. And that is when we have the group discussion, okay, the group discussion on several topics, okay. Please wait for a while for the topics and for the details, okay. So I think that's it for today. So thank you for your attention. See you later.